There are three main ways that we have of giving sets. A set is a collection of items. The items themselves are called elements. So we can list things out as long as we do not have too many items. A list can serve us perfectly fine. And what we would do in this particular case is we would have curvy brackets. We would have the list of items, each separated by a comma, and we would close that set with another curvy bracket. Preferably, we do not repeat any items. So if, for instance, we have A, we don't repeat. We just go ahead and say we've got A as part of our set. Let's list it once, call it a day. Also, the list of positive even numbers up to and including 10, 2, 4, 6, 8, 10. Slap them inside some curvy brackets, la-di-da. When our lists get longer, we sometimes might like to rely on what we call set builder notation. What we're trying to do here is give a description of what that set looks like. So to match up with those earlier two examples, a description of this first set here would be the set of vowels in the English language. In set builder notation, what we're going to do is basically say, here is a generic element. We'll use some sort of symbol to represent that. Then we either have a little vertical bar or a colon for the phrase such that. So this is going to now have a description following that will tell us what kinds of elements, what kinds of items are supposed to appear in that set. So this generic element, whatever it is, we're calling X generically, that is supposed to be a vowel. So that gives us a good enough description so that we would be able to tell, is this particular thing in the set? Is this particular thing not in the set? As far as the other example, in fact, I even just mentioned the one possible description of this a moment ago. Generic element, we'll call it Z, such that, using the colon this time, Z is an even number between 2 and 10, inclusive. The inclusive word there at the end tells me include the 2 and include the 10 in our set. So that would mean include the 2, include the other even numbers up to 10, include the 10, stop listing your even numbers at that stage. So we can do that as well. We also have some special sets before we get to the third option, which is far more popular as far as giving sets. Some of these special sets that we have, the natural numbers. So those would be the positive whole numbers that start with 1, the little dot, dot, dot in here referring to a particular pattern that would continue on, either continuing on forever, or if there was something at the very end that capped things off, we might stop there. But the natural numbers continue on forever, dot, 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 1, 2, 3, 4, 5, et cetera, et cetera, et cetera. Whole numbers, well, those take the natural numbers and slap in a 0. Integers, officially speaking, all the positive whole numbers. And then if I take those positive numbers and slap on negative signs, then I can have all of those negative whole numbers as well. Rational numbers takes care of all the numbers that can be written as a ratio, aka a fraction, where I have integers on the top, integers on the bottom, except for no 0 allowed on the bottom. No decimals allowed on the bottom. So we could say something like this as far as our set builder notation. The set of P over Q, where P and Q are integers, and Q is not 0. Excuse me. All the fun numbers like pi, the square root of 2, and even weirder ones. All the numbers that are real but are not already rational. So these are things that cannot be written as a terminating or a repeating decimal. That's another way of putting it. We have some inequality statements as well, just to kind of incorporate phrasing in words of what we might have. So less than, or we could also say exceeds or greater than, depending on how we're phrasing things. Greater than, exceeds is less than, just depending on how we phrase things, less than or equal to. We could say at most or no more than, greater than or equal to, no less than, at least. We've got all these different sorts of phrasings that we can use to get across the same sort of idea. A couple of ones that we don't necessarily use that often as far as working problems out, except for occasionally. We have the not equal to and the approximately equal to. Excuse me. The third and main type of set notation that we use is called interval notation. And since I already have a separate video that handles the interval notation, as well as one of our other topics here in this particular collection of topics, we've got solving linear inequalities. Well, a good chunk of that is already handled, so you can, at this time, pause this video, watch this other one, and then we can pick up with a few little extra things here. If we tag on a few little extra things to our discussion of interval notation and solving linear inequalities, what we have are two basic ways of putting sets together, the union and the intersection. The intersection is by far the more natural one to understand here. Like the intersection of two roads, this is where two roads would overlap, where they would meet. And sets would have that same sort of notion. This is where we would have things that are in common with both set A and set B. And so a handy way of doing this, for those of you that are visually inclined, yellow and blue make green. So we can kind of take advantage of that visual, the word and connecting to intersection. Yellow and blue make green. Where yellow and the blue overlap one another, they will create green color. So automatically those colors will help us identify what the intersection is. The union is, well, a little bit more of a stretch to try to explain in more practical terms, but the joke I like to make is that you take two people and you marry them, then they have engaged in a union, and so those two people have become one, and that one thing, a married couple, kind of greater than the original things were separately. So, yeah, I know, a bit of a stretch. Nonetheless, what we've got going on here is anything that's in A, we shake into a box. Anything that's in B, we shake into a box. So it's everything just combined together, and that gives us at least a little bit more of a practical feel for what's happening here. So we're going to lump everything together into a single set. The key word that can show up here that connects to the union is the word or. So if we consider a kind of coloring here to help us along the way, orange, if I color each set orange and then try to put everything together, well, everything that's colored orange is going to be in my answer. Let's see how that works with a couple of examples here. So one of each. In this first case, I've got a description of sets A, B, and C. A union C. I want to take everything in A, I want to take everything in C, I want to lump it together. And so I have drawings here with my number lines, and I'm going to copy those over off to the right-hand side. And I'm going to overlap them so that I can see how things appear. Now things appear here to have orange completely and totally covering everything in my number line. The orange from this first number line will cover the 6 that in the second number line wasn't included, but now it gets colored in as part of that first number line. And everything off to the left from the second number line, everything here we can see in this drawing, everything is getting colored in orange. So what we would have going on here seems to be that everything off to the left forever and ever, so parentheses negative infinity, everything off to the right, and everything in between, so positive infinity, parentheses to close that out. This would actually be our answer for the A union C. Similar sort of idea with the next example, where what I've got going on is going to be based on the intersection this time. So I would want to take the two of my number lines, slap them one on top of another, and what I can see here is that I start to get some green off to the left side. That green, for sure, is going to be off to the left, continuing on forever. So my parenthesis negative infinity. And that green seems to come all the way up to the -5. Now the -5 is not colored yellow, but it is colored in blue. If it's not colored yellow, then the -5 wouldn't turn green. So the -5 is not going to be part of my answer, where yellow and blue make green. So as it turns out, the answer that I'm getting here is actually just the same as this original picture of set B. Well, that's the way that it shakes out. Nonetheless, kind of the idea here is to try to show you how it can be very handy for us to use highlighters and number lines to help us figure out the union and the intersection problems. These can show up now in combination with the inequality problems that appeared in the earlier video. Quite literally where an and or an or words show up, but also a little bit more subtly like this next example, where what we've got is hidden underneath two separate inequalities that are linked together with the word and. So the intersection is kind of already built into play here, and we can extend our idea of working with equations and inequalities to say that if I have a situation like this, anything that I do in the middle must be done to the left and right, and I can switch that up as well. If I want to tinker with the left, I have to do the same thing in the middle and in the right. If I want to tinker with the right, anything I do has to be done in the middle and in the left as well. So looking at this particular problem and saying, well, to get started, we've got our variable showing up in the middle section. That's the only place that it does show up. So we will, excuse me, add 3 in the middle. If I do that in the middle, then I have to do that on the left and right, and that will give me a -5 on the far left. In the middle, that will give me a 5x, and on the right, that will give me a 15. Then I can take this, and in order to get the x by itself, I would want to divide. And if I divide in that middle section by 5, I will want to do the same thing in the left and in the right in order to come up with a -1 is less than x is less than or equal to 3. For the number line version of this particular answer, let's go ahead and put down those two key numbers that show up, the -1 and the 3. Based on the inequality symbol showing up here, -1 is less than. That means that the -1 will not be included excuse excuse me. And so, because I want numbers that are between these, the parenthesis that I need to have here is going to be like so. The negative 3, or excuse me, the positive 3, in front of it has a less than or equal to symbol, so that means I would want to use a bracket where the 3 appears, and the bracket that I want, again, to make sure that things are matching up and being colored correctly would be a bracket like so. And again, I want the things that are in the middle, so I would want to color in with my number line using any of my chosen colors. Pink is the most convenient for me. I have the number line version, and then from there I can much more quickly figure out the interval notation answer. So the interval notation answer, very directly coming from that number line, is going to begin on the far left, where I first have the color showing up, which would be right where the negative 1 appears, and I take the symbol directly from where that negative 1 appears, so my answer begins with the parentheses and the negative 1, comma in the middle there, and my pink color goes all the way up to the 3. The 3 has a bracket, which tells me the right-hand end, or the back end there of my interval notation answer is going to have a bracket. So that nice direct connection that I can try to use to come up with that. And as I mentioned just a few minutes ago, we can literally have the word and or the word or showing up. If we have the word and, yellow and blue make green, give us a nice handy way of trying to put things together. If we have the word or, color everything that we've got in orange and put things together. And so the gist of it would be that I have 2 or more separate inequality problems. I can work each one. I can represent each individual answer on a number line, and then I will put those number lines together either with the or the and words, either with the yellow and blue make green idea or with the orange idea. And that'll give me a way of putting together my overall answer. So like we did with those earlier problems, having this already worked out for us, what we can do is we can bring these number lines over. We can go ahead and get them overlapping with one another by moving things around, one on top of the other. And that'll help us figure out what our answer is. Yellow and blue make green. Where we see the green showing up is between the negative 2 and the 6. So right away, without any sort of extra thinking, we've got the negative 2 and the positive 6. Now we need to know exactly how do we put the introductory symbol, the opening symbol, and the final closing symbol onto our interval notation answer here. In the first drawing, I do officially have yellow where that bracket is. In the second drawing, I have blue, yellow, and blue make green, so that bracket is in fact good to go there. And so our answer will begin with the bracket in front of the negative 2. In the first of our drawings, the 6 would be colored yellow, but in the second, it would not be colored blue, so that means that the 6 would not be colored green overall, so the parenthesis there is actually still in effect. So we have those coming out. To quickly look at another one that also has the and showing up, we'd again take those 2 drawings. We would want to put them one on top of the other and see how things play out. Oop, didn't catch everything there. So putting those drawings one on top of the other. We see that the green we have starts at 0, goes up to 15 over 2. And if we can take for granted that the symbols are going to match up, and we can double check those based on our individual drawings. First one's yellow, second one is not blue, so the 0 is not included. That means that parenthesis in front of the 0 holds up. And for the 15 over 2, that is not colored in yellow, though it is colored in blue. That would not together be green. Therefore, the parenthesis after the 15 over 2 is also going to hold up there for us. So yellow and blue make green. If instead we had the word or showing up in between, just a couple of examples there to kind of hit that effect before we close things out for this discussion. Having those worked out separately and wanting to put them together into one picture means that we would have, from the look of things here, two separate pieces that make up our answer. Well, this is a little bit unusual, but this brings up the other place in which the union symbol appears. Every once in a while, we literally need to write one set as an answer. Our answer is supposed to be one set. But in this drawing, it appears to be two separate sets. Well, with a little math magic, we can just go ahead and consider the second set joined together with the first set. So, the stuff that's colored in orange over on the left side of our drawing, the stuff that's colored in orange on the right side of our drawing, because those are apparently separate by themselves, the left part of our color, the right part of our color. These two can be joined into one by just slapping the union symbol between them. That's the best option that I have of creating what can be viewed now as one big old answer. Kaboom, one big old answer. Here's this parentheses, negative infinity, comma, negative 2, bracket. Union, parentheses, 3, comma, infinity, parentheses. All of that's now considered one big gigantic set simply because I put the union in there. And I can get away with that only when I have two separate pieces. If these had overlapped at any point, then again, I can probably give a much more direct and shorter version. So this is only used as a last resort when we have two separated pieces of our answer that we want to officially consider one big answer. Let's see what happens in the second example, where again we have the same sort of basic idea, working each problem out separately. We now want to take these and put them together to see what happens with our orange coloring. So when we lay them one on top of the other, what seems to show up here is that our entire number line is colored in orange. Even though the 5 is not colored in orange in the top drawing, it is colored in orange in the second one, so the 5 is going to actually appear in our answer set. The 8 is colored orange in the first drawing, so it doesn't matter that it's not colored in orange in the second drawing. Overall, when it's all put together, the 8 does get colored in, so apparently I get to color everything in. The entire number line then would be the interval, parentheses, negative infinity, comma, infinity, parentheses. So we've got that way of trying to use the visual and the number lines to help us achieve the interval notation answers that we would want to come up with in these inequality problems.